The freezing point of a substance is defined as the temperature at which its solid phase is in dynamic equilibrium with its liquid phase. At the freezing point, the vapor pressure of the substance in its liquid phase is the same as the vapor pressure of the substance in its solid phase. When a non-volatile solute is added to a solvent, the freezing point of the solution gets lowered. According to Raoult's law, the vapor pressure of a solution containing a non-volatile solute is lower than that of the pure solvent, and therefore it would become equal to that of the solid solvent at a lower temperature. That is why the freezing point of a solvent decreases when a non-volatile solute is added to it. This can also be explained if we plot a graph of the variation of the vapor pressure of a pure solvent and solution as a function of temperature. On cooling, the vapor pressure of the pure solvent decreases along curve AB. At point B, the solid starts appearing. On further cooling, the vapor pressure decreases steeply along BC. This is because solids have lower vapor pressure than liquids. At point B, the liquid phase and the solid phase are in equilibrium and have the same vapor pressure. Therefore, B represents the freezing point Tf0 of the pure solvent. Also, at any given temperature, the vapor pressure of the solution is less than that of the solvent, and curve DE for the solution lies below that of the solvent. Curve DE meets the pure solvent curve at E. Therefore, E represents the freezing point Tf of the solution. As can be seen, Tf is lower than Tf0. Therefore, the difference delta Tf is called the depression in freezing point and can be written as delta Tf is equal to Tf0 minus Tf. The depression in freezing point depends upon the concentration of the solution. For dilute solutions, depression in the freezing point is directly proportional to molality m. Thus, delta Tf is equal to Kf into m, where Kf is known as the freezing point depression constant or molal depression constant or cryoscopic constant. Molal depression constant Kf can be defined as the depression in freezing point when 1 mole of solute is dissolved in 1 kg of solvent. The unit for Kf is Kelvin kilogram per mole. As Kf depends upon the nature of the solvent, its value is different for different solvents. The values of Kf can be calculated from this expression. In this expression, R stands for the gas constant, M1 stands for the molar mass of the solvent. Tf denotes the freezing point of the pure solvent. Remember that all these quantities are in Kelvin. Similarly, delta H fusion represents the enthalpy for the fusion of the solvent. If W2 grams of a solute with molar mass M2 is dissolved in W1 grams of a solvent. Then, molality M of the solution is given by W2 multiplied by 1000 divided by W1 multiplied by M2. Substituting this value of molality in the freezing point depression equation, we get depression in freezing point delta TF is equal to Kf multiplied by W2 multiplied by 1000 divided by W1 multiplied by M2. For molar mass of the solute, this equation can be written as M2 equal to Kf multiplied by W2 multiplied by 1000 divided by W1 multiplied by delta TF. Thus, the molar mass of a non-ionic solute can be calculated by studying the depression in freezing point. Let us now solve a numerical problem based on depression in freezing point. Calculate the mass of ascorbic acid, vitamin C, C6H8O6, to be dissolved in 75 grams of acetic acid to lower its melting point by 1.5 Kelvin. Kf is equal to 3.9 Kelvin kg per mole. The first step, as usual, is to list the given variables. W1 is equal to 75 grams. Delta TF is 1.5 Kelvin. Kf is 3.9 Kelvin kg per mole, and the molar mass of ascorbic acid is 176, while W2 needs to be calculated. Substituting the given values in the equation for depression of freezing point of a solvent and solving for W2, we get W2 is equal to 5.077 grams. That is, when 5.077 grams of ascorbic acid is dissolved in 75 grams of acetic acid, it lowers its melting point by 1.5 Kelvin. Let us look at some important applications of depression in freezing point. Running a car in sub-zero temperatures, even when the radiator is full of water, is possible due to the fact that a depression in the freezing point of water takes place when an appropriate amount of solute ethylene glycol called antifreeze is dissolved in it. Another important application is the use of common salt, that is, sodium chloride or even calcium chloride, to clear the snow on the roads. The addition of these solutes depresses the freezing point of water to such an extent that it cannot freeze at the prevailing temperature, and hence the snow melts off easily. Observe these processes carefully. Place some dried fruits and vegetables in water. They slowly swell up and return to their original form. When a raw mango is placed in concentrated salt solution, it loses water and shrivels into a pickle. Similarly, if we place wilted flowers in fresh water, they are revived. All these processes have one thing in common. There was a flow of water molecules either to or from the substance. Secondly, all the substances were bound by membranes. This phenomenon is called osmosis. Small solvent molecules like water can pass through the holes of these membranes, but bigger molecules like the solute are unable to pass through them. Such membranes, which are selectively permeable to only certain molecules, are known as semi-permeable membranes or SPM. These membranes can be of natural origin or synthetic origin. Vegetable membranes, which are found just under the outer skin, like in the onion, membranes found under the shell of an egg, a pig's bladder, or parchment are examples of natural membranes, while cellophane is an example of synthetic membrane. Osmosis can be defined as the spontaneous flow of solvent through a semi-permeable membrane from a pure solvent to a solution, or from a dilute solution to a concentrated solution. It is important to note that osmosis drives solvent molecules through a semi-permeable membrane from low solute concentrations to high solute concentrations. Osmosis ends when the solute concentration becomes equal on either side of the membrane and equilibrium is attained. The flow of solvent molecules from low concentration to high concentration can be stopped by applying some extra pressure on the high concentration side. The minimum pressure required to do so is known as the osmotic pressure of the solution. Thus, osmotic pressure pi of a solution is defined as the excess pressure that must be applied to a solution to prevent osmosis from taking place. Osmotic pressure, like other colligative properties, does not depend on the identity of the solute, but on its concentration. It has been found experimentally that osmotic pressure pi for dilute solutions is proportional to molarity C of the solution at a given temperature T. Thus, pi is equal to C multiplied by R multiplied by T, where R is the gas constant. If the solution contains N2 moles of solute in volume V, then C is equal to N2 divided by V. Therefore, pi is equal to N2 multiplied by R multiplied by T divided by V. If W2 grams of solute of molar mass M2 is present in the solution, then N2 is equal to W2 divided by M2. Substituting this value of N2 in the earlier equation, we get pi equal to W2 multiplied by R multiplied by T divided by M2 multiplied by V. Rearranging the equation for M2, we get M2 is equal to W2 multiplied by R multiplied by T divided by pi multiplied by V. This method of measurement of osmotic pressure is widely used to determine the molar masses of polymers and macromolecules, especially biomolecules, as they are generally unstable at higher temperatures and decompose before their boiling point is reached. This method has the advantage over other methods as osmotic pressure is measured around room temperature and the molarity of the solution is used instead of its molality. Let us now solve a numerical problem based on osmotic pressure. 1 liter of an aqueous solution of a protein contains 10 grams of the protein. The osmotic pressure of such a solution at 300 Kelvin is found to be 2 multiplied by 10 to the power minus 3 atmosphere. Calculate the molar mass of the protein. The given variables are W2 is equal to 10 grams, V is equal to 1 liter, T is equal to 300 Kelvin, and pi is equal to 2 multiplied by 10 to the power minus 3 atmosphere. M2 needs to be calculated. Also, R is equal to 0.082 liter atmosphere per Kelvin per mole. Substituting these values in the equation, M2 is equal to W2 multiplied by R multiplied by T divided by pi multiplied by V. And solving, we get M2 is equal to 1,23,000 grams per mole. In other words, the molar mass of the protein is 1,23,000 grams per mole. Let us consider two solutions with concentrations C1 and C2 at temperature T. Then osmotic pressure for the first solution, pi 1, is equal to C1 multiplied by R multiplied by T. While osmotic pressure for the second solution, pi 2, is equal to C2 multiplied by R multiplied by T. Now, if the solutions have the same concentrations, that is, if C1 is equal to C2, then pi 1 becomes equal to pi 2. It means that equimolar solutions at the same temperature have the same osmotic pressure. Such solutions with the same osmotic pressure at a given temperature are called isotonic solutions. When such solutions are separated by a semi-permeable membrane, no osmosis occurs between them. It is because of this reason that in an intravenous injection of 0.9% mass by volume sodium chloride solution, called normal saline solution, is used, since it is isotonic with the fluid inside the red blood cells. A pure sodium chloride solution with the concentration more than 0.9% mass by volume is called a hypertonic solution. And red blood cells shrink when placed in this solution. On the other hand, a pure sodium chloride solution with a concentration less than 0.9% mass by volume is called a hypertonic solution. And red blood cells swell up and may even burst when placed in this solution. It is important to note that a high intake of salt in the diet can lead to a higher concentration of fluids in the body tissues because of osmosis. This will result in swelling and puffiness of body parts, which is known as edema. It is of interest to mention that if a pressure greater than osmotic pressure is applied on a solution, then the solvent will flow from the solution to the pure solvent through the semi-permeable membrane. This process is known as reverse osmosis and is often used for the desalination of seawater for getting fresh drinking water. Desalination of seawater is carried out using a cellulose acetate semi-permeable membrane placed over a suitable support. This cellulose acetate membrane allows the passage of only water molecules through it and is impermeable to the salts and other impurities present in seawater, thus making it fit for drinking. You know that colligative properties are properties that depend solely on the number of dissolved solute particles and not on their identity or nature. Various relations derived for colligative properties hold good only for solutions of non-electrolytes, as there is no change in the molecular state of the solute. When a solute undergoes dissociation or association in a solution, then the number of particles of the solute in the solution increases or decreases respectively. Thus, the colligative property changes accordingly and we get abnormal results. Inorganic acids, bases, and salts undergo dissociation either completely or to some extent in an aqueous solution. For example, if 1 mole of potassium chloride, KCl, is dissolved in water, then the aqueous solution contains 1 mole of potassium ions and 1 mole of chloride ions. In such cases, the number of effective particles in the solution increases, and therefore, the observed colligative properties like osmotic pressure, elevation of boiling point, and depression of freezing point are much higher than those calculated on the basis of undissociated single molecules. Further, as molar mass is inversely proportional to the colligative property, the experimentally determined molar mass will always be lower than the true value for dissociation. For KCl, as the number of particles becomes double, the observed colligative property is double than the expected value, while the observed molar mass is half the expected value. That is, 74.5 grams divided by 2, which is equal to 37.25 grams. Similarly, there are many organic solutes that undergo association in a non-aqueous solution. That is, 2 or more molecules of the solute associate to form a bigger molecule. For example, ethanoic acid in benzene exists as a dimer due to hydrogen bonding. Thus, the number of effective molecules or particles in the solution decreases. If the association of ethanoic acid is assumed to be complete, then the observed value of the colligative property will be half, and the molecular mass would be double the expected value. When the molecular mass of a substance, as determined by studying any of the colligative properties, comes out to be different than the theoretically expected value, the substance is said to show abnormal molecular mass. In order to account for all such abnormalities, Dutch chemist J. H. van 't Hoff, in the year 1880, introduced a factor I known as van 't Hoff's factor, which represents the extent of association or dissociation of a solute. Quantitatively, van 't Hoff's factor I is defined as the ratio of the observed colligative property to the calculated colligative property. Thus, the expression for I can be written as I equal to the observed colligative property divided by the calculated colligative property. Now, since colligative property is inversely proportional to molar mass, I, in terms of molar mass, becomes I is equal to normal or calculated molar mass MC divided by abnormal or observed molar mass MO. Further, as the colligative property depends directly on the number of particles present in a solution, it can also be written as I is equal to total number of moles of particles after association or dissociation divided by number of moles of particles before association or dissociation. Note here that the calculated colligative property takes into account the assumption that the non-volatile solute has undergone neither association nor dissociation. The value of Van 't Hoff's factor is less than 1 if there is association of the solute in a solution, and is greater than 1 if there is dissociation of the solute in a solution. For substances that undergo neither dissociation nor association in a solution, I is always unity. If a solute undergoes 100% dissociation, then Van 't Hoff's factor is equal to the number of ions produced from one molecule of the solute. For example, the value of I is 2 for aqueous KCl. This signifies that KCl has dissociated completely into potassium and chloride ions. The value of I equal to nearly 0.5 for ethanoic acid in benzene, which signifies that nearly the entire ethanoic acid has undergone association and exists as a dimer. The modified equations for colligative properties using the Van 't Hoff's factor can therefore be written as relative lowering of the vapor pressure of solvent P1 naught minus P1 divided by P1 naught is equal to I multiplied by N2 divided by N1. Elevation of boiling point delta TB is equal to I multiplied by KB multiplied by M. Depression of freezing point delta TF is equal to I multiplied by KF multiplied by M. Lastly, the osmotic pressure of a solution pi is equal to I multiplied by N2 multiplied by R multiplied by T divided by V. The degree of association as well as the degree of dissociation are represented by the letter alpha. Let us now derive a relation between Van 't Hoff's factor I and the degree of association alpha. The degree of association of a substance, alpha, is defined as the fraction of the total substance that exists in the form of associated molecules. That is, the number of moles associated divided by the total number of moles taken. Consider 1 mole of solute A dissolved in a given amount of solvent. And suppose that n molecules of A associate to form associated molecule AN, and an equilibrium gets established between Na and associated molecule AN. If alpha is the degree of association of the solute, then at equilibrium 1 minus alpha moles of A are left in unassociated form, while alpha divided by n moles of AN are present in associated form. Therefore, the total number of moles of particles after association is equal to 1 minus alpha plus alpha divided by n. If there is no association, then the number of particles is equal to 1. Substituting the values of the number of particles in the relation I is equal to total number of moles of particles after association or dissociation divided by the number of moles of particle before association or dissociation. We get I is equal to 1 minus alpha plus alpha divided by n divided by 1. On simplifying for alpha, we get alpha is equal to 1 minus I multiplied by n minus 1. Thus, if the value of n and Van 't Hoff factor I is known, then the degree of association, alpha, can be calculated. On the same lines, let us now derive a relation between Van 't Hoff's factor I and degree of dissociation, alpha. The degree of dissociation of a substance, alpha, is defined as the fraction of the total substance that undergoes dissociation. That is, alpha is equal to the number of moles dissociated divided by the total number of moles taken. Suppose one molecule of electrolyte A gives n number of ions on complete dissociation. That is, in general, A dissociates to give n1 moles of B plus n2 moles of C plus and so on, such that n1 plus n2 plus and so on is equal to n. If we start with 1 mole of the solute at equilibrium, we have 1 minus alpha moles of the undissociated molecules and n alpha moles of the ions. Thus, the total number of particles present at equilibrium is equal to 1 minus alpha plus n alpha, or 1 plus n minus 1 alpha. Substituting the values of the number of particles in the relation, I is equal to total number of moles of particles after association or dissociation divided by number of moles of particles before association or dissociation. We get I is equal to 1 plus n minus 1 alpha divided by 1. On rearranging, we get alpha is equal to I minus 1 divided by n minus 1. Knowing the value of I from the colligative property measurements, the degree of dissociation, alpha, can be calculated. Let us now solve a numerical problem based on the association property of a solute. Acetic acid CH3COOH associates in benzene to form a dimer. 1.65 grams of acetic acid, when dissolved in 100 grams of benzene, elevates the boiling point of benzene by 0.36 Kelvin. Calculate Van 't Hoff's factor and also the degree of association of acetic acid. Kb for benzene is 2.57 Kelvin kilogram per mole. The first step is to list the given variables. W2 is equal to 1.65 grams. W1 is equal to 100 grams. Delta Tb is equal to 0.36 Kelvin. Kb for benzene is 2.57 Kelvin kilogram per mole. Molar mass of acetic acid M2 is equal to 60 grams. Van 't Hoff's factor I and degree of association needs to be calculated. Let us first calculate Van 't Hoff's factor I. Substitute these values in the modified equation for elevation in boiling point. Elevation of boiling point delta Tb is equal to I multiplied by Kb multiplied by W2 multiplied by 1000 divided by M2 multiplied by W1. On solving for I, we get Van 't Hoff's factor I is equal to 0.5093. Substituting for I in the equation, degree of association alpha is equal to 1 minus I multiplied by n minus 1. Now, n for acetic acid is 2 as it exists as a dimer. On solving, we get degree of association alpha is equal to 0.98. Let us now solve a numerical problem based on the dissociation property of the solute. A solution containing 1.23 grams of calcium nitrate in 10 grams of water boils at 100.97 degrees centigrade. Calculate the degree of dissociation of the salt. Kb for water is 0.52 Kelvin kilogram per mole. The first step is to list the given variables. W2 is equal to 1.23 grams. W1 is equal to 10 grams. Delta Tb is equal to 100.97 degrees centigrade minus 100 degrees centigrade, which is equal to 0.97 degrees centigrade. Kb for water is 0.52 Kelvin kilogram per mole. Molar mass of calcium nitrate, M2, is equal to 164 grams. The degree of dissociation needs to be calculated. For finding the degree of dissociation of the salt, we first need to calculate Van 't Hoff's factor, I. Substitute these values in the modified equation for elevation and boiling point. Elevation of boiling point delta Tb is equal to I multiplied by Kb multiplied by W2 multiplied by 1000 divided by M2 multiplied by W1. On solving for I, we get Van 't Hoff's factor, I, is equal to 2.48. Substituting for I in the equation, degree of dissociation alpha is equal to I minus 1 divided by N minus 1. Now, N for calcium nitrate is 3. On solving, we get the degree of dissociation. Alpha is equal to 0.74.